So in this video, also belonging to the series of videos associated with this book, I'm going to talk about a multiple linear regression. Then we will start again doing exploratory data analysis, as it was indicated in a previous video, and then move into the frequentist and Bayesian model fittings. All the codes to run this analysis are available in the book website. So first, a general gist or a general idea for what this method is about. So the goal here is to find not the best line, but the best plane that relates a numerical response variable y with k explanatory variables x, here illustrated with two explanatory variables x1 and x2. So we have a three-dimensional space in which we have the base plane that fits this three-dimensional cloud of points. Here noting the intercept when both explanatory variables are equal to 0, the partial slope beta 1 for the explanatory variable 1, and the partial slope beta 2 for the explanatory variable x2. So this is, of course, another special case of the general lineal model, or if you wish, it's a generalization of the simple linear regression, which is the same thing. So the statistical model, again, is that the response variable has a normal distribution with a given mean and a given variance, and the mean is equal to the linearly related by this equation, with the I corresponds to the partial slopes and the explanatory variables xi. So, given that the model now involves several explanatory variables, we must now think in a few important issues. So, first of all, is how many and which explanatory variables should we include in the model? So, should we include everything, including the kitchen sink, or should we include a few variables related to specific hypotheses that we have? I would strongly suggest the latter, but of course the choice is yours. So, should explanatory variables to be included only as simple effects, or should be included as the interactions? Interactions referred to are brutally and simply referred to as the product of these two numerical explanatory variables. The explanatory data analysis. So we first import the data. The goal of the analysis is to relate the average annual concentration of SO2, sulfur dioxide, a contaminant, related to the number of industrial companies, the population size, and the size of climatic variables in 47 American cities in the 1970s. So, as in the video 5, the previous one, we compare the two candidate probability distributions for y using the cumulative distribution function and the QQ plots, both obtained with the package fit distribution plus. So here is the density curve of the response variable showing an asymmetric shape, and here is the cumulative distribution function for the two candidate distributions to model it, which are the normal in black and log normal in gray, and here are the QQ plots, and it's pretty clear that the best fitting distribution is log normal. So when the conclusion is that, of course, it's log normal, and we are going to use the following statistical identity, which is that when a given variable has a log normal distribution, the log of that response variable has a normal distribution, and in this way the log of the SO2 concentration would be our response variable in all models we are going to fit, because we are considering this as being part of the general linear model, which is what we are explaining now. So now we need to answer the question of whether the response variable concentration of the log of the concentration of SO2 is related to all the explanatory variables in the set, for which we made a matrix of plots. In the diagonal, we have the density curves for each of these variables. Here we have the response variable log SO2, and so in the bottom row we have in the vertical axis the log of the SO2 against temperature here. There is a declining relationship. The log of the SO2 in relationship with the number of manufacturing enterprises against the population of in 1970s, and the other climatic variables showing virtually no relationship whatsoever. In the upper triangular part of the plot are the correlations, the Pearson correlations between pairs of variables. Another important thing to consider in this type of model is here in this triangular set that I am highlighting is whether there are any pair of numerical explanatory variables that are strongly correlated, and the answer is no. By strongly we mean that the absolute value of the correlation coefficient is at least 0.7. If had we had a correlation, a pair of variables with a very high correlation, my suggestion, as is discussed in the book, would be to pick one of the two, the one that is more closely related to a mechanism that would link it to the response variable. So the numerical explanatory variables are all measured in different units, which hinders the comparison of the numerical comparisons of their partial slopes. So scaling the explanatory variables to have mean 0 and standard deviation of 1 solves the problem. By putting them in a common scale, allowing to gauge the relative importance. So when the explanatory variables are in the original scales, the intercept in this case would be the mean of the log SO2 in a city of population 0, wind 0, precipitation 0, that is a city that does not exist. And the partial slopes, as I alluded before, could not be numerically compared. So what we do here is we use the command scale, and here we select the explanatory variables by their names, and by putting center equal true, we subtract the mean. By putting scale equal true, we divide by the standard deviation, and we combine that with a new variable, which is the log of the SO2 that we had already prepared, and we generate now a new data frame that is related to the previous data frame resulting from the importing of the data. So when the explanatory variables are scaled, the intercept now becomes the mean of the log SO2 for a city of average population, average wind, average number of manufacturing enterprises, and so on. That is, it would be the mean of the SO2 for a typical city. And the partial slopes now are the rate of change in the mean of the SO2, log SO2, for a change in one standard deviation of each of the explanatory variables. So the frequentist model fitting. So we simply proceed much in the same way as in the simple linear regression, simply entering all the explanatory variables obtained from the data frame where we had all these variables scaled. We LM meaning linear model, and we save the result in the object M2S. The statistical model, as usual, can be written in the following way for the reasons explained in the previous video. So the summary of the model is the following. So here we have the descriptive statistics of the residuals. Here we have the intercept, which is, in this case, because the variables are standardized, this is the mean of the log of SO2 for a city of average temperature, average number of enterprises, average population size, average wind speed, average precipitation, and average number of rainy days. So again, this standard error is the precision with which this sampling intercept estimates the population intercept, and this is p-value here is just saying that this number is significantly different from 0, which is of no interest whatsoever. So here we have minus 0.35 is a partial slope for the temperature. This is its standard error, and this p-value says that this slope with this partial slope with this standard error is significantly different from 0. Okay, here we also have a few other things, which is the estimate of the standard deviation, not the variance, the standard deviation of the response variable, which is here the log of the SO2. We square this and we obtain an estimate of the variance, and we also obtain the adjusted R-square, which is a proportion of the variation in the response variable explained by the model that we have just fitted. So a change in 1 unit in the population size, 1 unit in this case, because the variable start scale means 1 standard deviation, a change in 579 people would lead to a decrease because this is negative, of 0.022 in the mean of the response variable. So again, because all these coefficients are in the same scale, we could compare, for instance, the two variables that happen to have partial slopes significantly different from 0, one being mean temperature and the other being the number of manufacturing enterprises. And so we can take the ratio of these two coefficients that are in the same scale and say that one of the variables, temperature, is 34% more important than the other in affecting the mean of the response variable. And this is regardless of their statistical significance or lack of thereof. So we use, again, the package Bloom to gather the input for the residual analysis. Again, showing here only the first line. There are as many lines as cities we have in our data frame. So we have the response variables, all the explanatory variables, and the rest of the input needed in order to make the residual analysis. This residual analysis provides a series of plots, probably too many. There are 9 plots. One is the residuals against the fitted values. Again, then we have the residuals against all the explanatory variables in the plots B, C, D, E, F, and G. Okay, so let's interpret a few, not all. So first of all, let's disregard a little bit the 2 points at the extreme and consider only the central part. So we see the variation in the negative part of the residuals is roughly of the same, goes from 0 to -1 and from 0 to +1. This is looks more or less like a random scatter. The same would seem to be the case when we compare the residuals against the temperature. When we compare the residuals against, for instance, either the number of manufacturing enterprises or the average wind speed, we should not interpret the right-hand side of each of these plots because there are only a few points. So let's focus on the part where we have information. And this actually does look like a random scatter as it does in this place. The points are just compressed simply because the scale is spread along this axis. So the residuals seem to have a normal distribution, as they should when a model fits well to the data, and there are a few data points, perhaps 1, 2, 3, 4 data points that we may look as relatively important. Perhaps this corresponds to these residuals that are somewhat a little bit extreme compared to the others. So the model has a decent, perhaps reasonable fit to the data. It's not excellent by any means. In order to communicate the results, we can first of all obtain with the command tidy a table, a type of data frame with the parameter estimates under 95% confidence intervals. This is perhaps better presented as a plot without the intercept. This just summarizes the effect of the variables. So these are the partial slopes for all the variables, and the bars correspond to the 95% confidence intervals of them. We can also obtain the conditional curve The point here is that our model has 6 explanatory variables. To make a full conditional curve in now 7 dimensions, 6 explanatory variables plus the response variable, we would need to provide or decide on the values for all 6 variables. Or I chose to make something simpler to illustrate the power of these ideas. And so I selected only the values of the 2 variables having large effects, meaning temperature. I selected all values of temperature. Remember that this variable is scaled. And for the manufacturer enterprises, I didn't select all the variables. I selected 3 of them. Whereas for the rest of the variables, their values are set to 0, meaning to their means. And with this table pred.m2s, we can generate a plot showing the predicted mean and the plus or minus 1 standard deviation of the other variable, meaning the number of manufacturers.
So now we are going to proceed to fit the multiple linear regression, the Bayesian model fitting. So again, I recall the the statistical model, which is that the log of the SO2 concentration, sulfur dioxide concentration in the air, has a normal distribution whose mean is explained by a linear combination of the explanatory variables with an additional variance around the mean that reflects the unexplained variation. So the first thing that we are going to do is to use the command get prior of the package BRMS, that once we write the statistical model, the same that we used in the frequentist fitting, indicating that the family, we are going to use family Gaussian. We now have all the priors that need to be set. We need to set a prior for the intercept. We need to set a prior for each of the partial slope for the explanatory variables and for the sigma, that is the standard deviation around the mean. Notice that we can actually fit, we are not going to do it, but we could actually fit different prior for different explanatory variable, for the slopes of the different explanatory variables. So we are simply going to state that the intercept is we are going to define a normal prior centered on 0, meaning that with a standard deviation of 4, meaning that 95% of the plausible values of the intercept will be between -8 and +8. For the slopes, we are going to define a sort of more informative prior with a normal distribution centered at 0 and with a standard deviation of 2, meaning that we expect slopes to be between 95% of the slopes to be between -4 and +4. And for the Cauchy distribution, we again use for the sigma, the standard deviation, we are going to use a half Cauchy distribution as we did in the previous video. So we are going to visualize the priors, and this essentially reflects what I just mentioned reflects in the picture what I just mentioned in words. So our model then is we use the same syntax that we used before, as using the priors that we defined. This is the same statistical model. The response variable is results from the linear effects of the explanatory variables. Family Gaussian prior equal prior M2, that vector of values that we include. We are going to use 3 chains. We are going to parallelize the calculations in order to increase their speed. We are going to use a warm-up of 1000 iterations that are going to be thrown away, and we are going to use a thin of 3, which means that for every third value that is selected, that the chains are going to potentially retain only every third value that is going to be explored by the chains. This is an important feature to reduce the autocorrelation in the parameter estimates that we can obtain because we are using a Markov chain in order to get in order to generate the successive values. So this may be of interest in other models. It will not be of interest in this one, but at least I wanted to mention the existence of this possibility. So the summary of the model is as follows. Again, we have the everything that is related to the posterior distribution, meaning the means, standard deviation of the posterior distribution of each of the parameters, the intercept and the standard slopes, and then the partial slopes, and the 95% credible intervals. So this means that the mean of the slope of temperature is 0.35 with a credible interval, 95% credible interval going between minus 0.64 to minus 0.05. So remember that all these variables were standardized prior to the analysis, and therefore this partial slope of minus 0.35 means that an increase of one standard deviation of the temperature leads to a decline of the mean log SO2 of minus 0.35 units. And then we have also, of course, again, the metrics related to the convergence of the chain that we are going to first evaluate in different plots in what follows. So the posterior distributions. So first, let's have a look at the posterior distributions of the three chains. They are not identical, they need not be, but they are fairly similar, which suggests that the three chains have converged to a common stationary posterior distribution for each of the parameters. If this was not the case, we could make more iterations. That is, instead of doing 3,000, we could make 10,000. We could change some of the parameters of the simulations. We can also check the degree of mixing of the chains. We do not see that one of the chains got stuck in very high or very low parameter values for very many of the iterations, and therefore we consider this an indication of a good mixing of the chains. The autocorrelation of the sample estimates for each of the parameters is fairly good, since all the values are in the range between 0.1 and minus 0.1 in correlation, which is quite close to for the three chains, which is quite close to statistical independence. If we did not observe, had we observed actually a very high correlation, say 0.3, 0.4 or more for one of the parameters, one or several of the parameters in some of the chains, we could increase the thin parameter of the setup of the model. That's the importance of knowing what this does. The posterior distributions, we can also plot them, and are now showing for the posterior distribution, showing the 95% credible interval in blue, and the line in dark blue corresponds to the mean of the posterior distributions. Notice the wiggly aspect of these density functions, showing that these were obtained by simulation and they are not theoretical curves. So we can also reflect this in a probably better and simpler way in terms of the mean of the posterior distribution. In dark blue, the 50% credible interval, and in light blue, the 95% credible interval of each of the parameters. One possibility to improve this graph is to not plot the sigma, because it's far away in the scale, or to make a break in order to have a very viewing of the credible intervals of all the parameters. We obtain again the Bayesian R-square with its standard error and the 95% credible intervals. So the model explains 51% or nearly 52% of the variation of the response variable, which happens to be log SO2, not SO2, log SO2. We are going to assess the goodness of fit of the data through the residual analysis, for which we obtain the probability distributions the posterior distributions of the Pearson residuals and of the fitted values, in the same way that we did in the previous video of linear simple linear regression. This is for the residuals, and this is for the fitted values. Notice that we put summary equal true, and in this case it provides the means of the posterior distribution for each of the residuals and for each of the fitted values for all the data points in our data set. And with this we make the following set of plots. So the first plot in the top left shows the residuals against the fitted values, showing essentially no discernible trend. So I'll focus again on the area where we had many points. Okay, and the plots between B, C, D, E, and F corresponds to the residuals, the mean of the residuals against the explanatory variables. For instance, let's not pay any attention whatsoever to the right hand side of the plot F, because it's just driven by 2 points out of 47. So let's look at, instead of the 45 points, and see that it's a similar scatter in the positive and negative side and without any obvious discernible trend. Similarly, we could do the same comment for the plot D, reflecting the population the average of the Pearson residuals against the population size in 1970. Only the left hand side of the plot has some information, and the residuals happen to have a normal distribution as it should. So we conclude that the model has a reasonably good fit to the data. The final point is communicating the model results, for which we are going to use the command conditional effects of the library of the package BRMS, which generates a sixth of at least 6 data frames, one for each of the explanatory variables, out of which we made the following plots. So this is a plot showing the predicted effect of temperature on standardized, on the log SO2, while having the rest of the explanatory variables set at 0, meaning that by setting them to zero, we set them, this 0 corresponds to the mean value. So we can also see, for instance, in some of the plots, in the plots C and D, that the width, the uncertainty, is a lot bigger for large values of population size and for large values of average wind speed, and this is simply related to the absence of points in our data set having large cities or large average speeds. If you remember, in the plot of the average wind speed, there were only 2 points, and therefore there has to be a great deal of uncertainty on the predicted values, on the conditional curves for this variable. So this concludes this video in which I talked about multiple linear regression. We did, as usual, the exploratory data analysis, the frequentist fitting and the Bayesian fitting, and all the codes and the data necessary to run this analysis can be found in the book website. I hope you found this video of interest, and keep tuned for more videos. Bye then.